Okay, thank you, Barry. Hi, everybody. Welcome to the August New York JavaSIG meeting. And it's nice to see some hardcore people in the month of August to come to a Java user group meeting. So that's really, really cool. So before I turn everything over to Simon Ritter here from Azul, I want to make an announcement. So going forward, Terra Sky has agreed to sponsor the New York JavaSIG. So we're going to be meeting here every month going on for the rest of the year. So thank you very much to Terra Sky. That's awesome. Yes, Gene.
We should mention August, October rather, so people don't confuse their own building.
I will. I'll send an invite out to everybody. I wanted to ask one question. So how many people are not using an AI to do coding? I'm assuming everybody is using. You're not. Oh, you're not coding. Well, who is not using the AI tool to do coding? Okay. So basically, most of you. How many people are using it in the IDE? How many people are not using that from command line? Oh. Well, either using it from the IDE or the command line. Both. Okay. That's interesting. Okay. Just curious. Because I'm developing a course for young students on using it from the command lines. I'm curious if you're. I think we have a speaker coming up talking about like using from the command line and saying like drop your IDE, but that's a couple of months from now. Okay, so we're very lucky to have Simon Ritter here, co-CTO, or is it deputy CTO from Azul Systems. He happened to be in town, so we invited him here. This is fantastic. So thank you, Simon.
Sure. Right, yes, thank you. Good evening. I have to say it's a real pleasure to be here again, because I can't remember. I've been to New York JavaSIG, but it's been a while.
Yes, quite a while.
Yes. But yeah, it's great to be here. So quick question. So who has heard of Azul? Okay, so not everybody. Okay, well, I'll talk a little bit about what Azul does later. But yes, I'm deputy CTO. I've been involved in Java really almost from the beginning. I actually joined Sun Microsystems in February of 1996, which was about the same time that JDK 1.0 came out, and I followed Java all the way through the Sun years, got acquired by Oracle as part of the Sun acquisition, did 5 years at Oracle, and then I've been at Azul for the last, goodness me, nearly 10 and a half years. So yes, lots of history with Java. So what I'm going to do today is talk about some modern Java puzzlers. And this is an audience participation session. Don't be worried, it doesn't involve lots of participation. All you have to do is raise your hand. That's it. So you get to vote on what you think happens with the code that I'm going to show you. And the idea behind this is I'm going to show you a sequence as a piece of code, and most of them are very short, only a few lines of code. And we're going to start easy, ease you into it, and you'll think, okay, yeah, I know the answer to that. That's all easy. Yep, I can do that. And then we'll gradually kind of build up into some more tricky ones. And we'll get to a crescendo where we'll really kind of make your brain think, oh, what am I talking about here? And there are some interesting situations. Now, before I start, I have to provide a disclaimer. And that disclaimer is that this is most definitely intended to be a fun session. It is intended to be educational. It is not intended to be a critique of the design of the language features that we're going to be talking about. Because when I was putting this together, there were some situations where I got a little bit confused myself, and I needed some answers. And so I started talking to Brian Gertz, who's the chief architect for the JDK. I was also talking to Gavin Bierman, who's responsible for some of the features we're going to talk about. And Brian was a little bit sort of hesitant. And he said, I don't like puzzle sessions because people tend to like come up with these very obscure kind of combinations of things, and they use like special characters and they do weird things, and it doesn't really reflect well on the language. And so I've tried to be as careful as I can about not doing that. And what we're going to do is we're going to talk about situations that could potentially happen in your code, realistic situations. There are a few which I would say are realistic situations in that you can do this, but you shouldn't. And we'll explain why as we go through. So like I say, it's very much not intended to be a critique of language features and their design. I have nothing but respect for people like Brian and Gavin and Alex Buckley as well. Oh my goodness, Alex Buckley, who is responsible for the maintenance of the Java SE specification. And when you look at what you have to do in terms of putting things together for that specification, it is not an easy job. Right, so what also do I mean by modern Java? Java has been around for over 30 years now, so what are we really talking about in terms of modern? What I'm going to talk about here is stuff that has been added through Project Amber. Project Amber is one of the sort of bigger projects within OpenJDK, along with things like Babylon and Panama, and we got other ones like that. Valhalla, which is the big one, of course, that's coming out soon. And what we're going to do is we're going to focus on certain parts of that. So we're going to talk a lot about patterns as they're applied in Java. We're going to talk about switch expressions, because there's a lot of interesting detail there. And we're going to talk about where you can mix primitives and reference types in both patterns and switch expressions. So that is the area that we're going to look at. Right, section 1, which I have described as exhausted by exhaustive. First, puzzle. Right, so I have a piece of code here. Like I said, these are very small sections of code, and we have to think about what's happening. So I have a method that returns an int x, and then I'm going to use the switch expression, and I'm going to switch on x, and I'm going to have a case for 0, which returns 0, and a case for 2, 4, and 6, which returns even. Okay, so my question to you as the audience is, do you think this will compile? Who thinks it will? Nobody. Okay, who thinks it won't? Okay, pretty much everybody thinks it won't compile. Well, that's good, because you're right. So like I said, we're going to start easy. So looking at this, it's fairly easy to say this won't compile. The reason it won't compile is because it is not exhaustive. It doesn't cover all possible values that we could pass in. So if I pass 1 or 1,000 or 42, I won't get a result, so it won't compile. Now this was a deliberate decision on the part of the developers of this in the way that they approached it. Because you could have quite easily argued, well, actually, you could compile that code. There's nothing logically wrong with it, in the sense that you could say, well, I only want to deal with 0, 2, 4, and 6. But when they came to design this feature, they said, actually, to try and eliminate as many possible errors as possible at compile time, we're going to enforce the idea that you have to deal with all possible values. And that seems to be a fairly logical thing to do, because if you forget to put something in, then it will actually get caught by the compiler in terms of not dealing with all possible values. Right, so if I add a default case to this, and I say other, who thinks this will compile now? Yes, it will, because it now deals with all possible values. Obviously, if it's not 0, 2, 4, or 6, the default case will catch it and we'll get a value back from that. Okay, nothing terribly exciting so far. Like I said, bear with me. The first couple are very easy, but we do move on. Right, now let's deal with the situation where we've got our int, which we're going to get value. Now we're going to have a string d, which we'll assign a null to make sure that it is assigned a value. And then we will use a switch statement, different to a switch expression, a switch statement. So in this case, what we're going to do is, in this situation, case 0, we will assign 0 to d, and we will assign even if we get 2, 4, and 6. So who thinks this will compile? Okay, a few people. Who thinks it won't compile? Okay, yes, it will compile. And the reason it will compile, even though it is not exhaustive, is because the switch statement already existed in Java. And the switch statement because when Java was initially designed, a lot of the syntax of the language was taken directly from C. If you look at the way switch works in C, you will find it doesn't have to be exhaustive. If we suddenly decided that actually we were going to now enforce exhaustiveness on a switch statement, that would break a lot of backwards compatibility, because people have written code where they haven't made it exhaustive, and so that code would no longer compile if we had that situation. So obviously we can see that there's a bit of a divergence. We've got the switch statement, which doesn't have to be exhaustive, and we've got the switch expression, which does have to be exhaustive. Okay. What about if we do this? We have case 0. Now, we're going to be a little bit different here, because remember, in this case, we're actually going to change it so that we have an integer wrapper class. So now we've got a reference type rather than a primitive. Now we're going to switch on X, and we're going to have a case for 0, case for 2, 4, and 6, and a case for null. Right. So who thinks this will compile? Okay. A few people. Who thinks it won't compile? Okay, so now we're starting to see a bit of a divergence in terms of the audience. This is good, you see, because like everybody's, oh, hang on. The answer is no, it won't. It will not compile because it is not exhaustive. Even though this is a switch statement, and I just said that with a switch statement, it doesn't need to be exhaustive. In this situation, a switch statement does need to be exhaustive because this will not compile. How does that work? And the reality behind this situation is that this is an enhanced switch statement. So we actually have 3 different types of switch in Java. We have the switch statement, the enhanced switch statement, and the switch expression. What is an enhanced switch statement? Well, it's one that uses features which have been added at the same time that the switch expression was added. Prior to when the switch expression was included in Java, you couldn't have a case for null because we didn't have the ability to test types. We could use primitives, we could use strings, we could use enumerations, but we couldn't use types. So that was in the introduction when we added pattern matching in switch, and so we couldn't use case null before. What the developers said is we really want to have exhaustiveness for switch completely. So even though this is a switch statement, they said because you couldn't write this code in the past, it won't break backwards compatibility. So we will enforce the exhaustiveness where you have a situation that you're using something which couldn't have been written before. So that's the reason we enforce that, and that code will not compile. Right, now let's look at enumerations. I have here an enumeration which I have called very innovatively AB. It has 2 values, A and B. And now what I'm going to do is I'm going to test that, and I'm going to have a switch expression which is going to switch on a value AB, and it's got a case for A, and it's got a case for B. Who thinks this will compile? Okay, who thinks it won't compile? Ooh, okay, a few people. This is good. Definitely seeing a bit of a, and some people not voting. So people are starting to think, oh, I don't know what the answer is. Well, this will compile because it is exhaustive. I have a value A and a value B in my enumeration, and I have a case A and a case B. So it is exhaustive. It covers all possible values in that enumeration. What about if I do this? And I say, okay, I'm going to have my same enumeration with AB, but now I'm going to use the switch statement, and I'm going to return A and return B. And another little sort of aside in terms of the way this works is that you have to put braces around the return, because the way that they define the arrow operator is that you have to have, now see if I get this right, because you have to remember, you have to have a statement block afterwards. You can't just have something on its own. You can do things like print, but you can't do a return. So you have to put the return in braces to make it into a block of code, and then that will work. But I digress. It has a return A and a return B. So again, you would think to yourself, okay, we're doing a switch statement, and we know that switch statements don't have to be exhaustive, but you think this is exhaustive. So who thinks this will compile? Okay, a few people. Who thinks it won't compile? Now we're getting down to like there's less than, not everybody's voting now. This is good. Right, so the answer is it will not compile. And the error message that you get is that this has a missing return statement. Hang on, where is the missing return statement? If I have an enumeration of A and B, and I've got a case for A and a case for B, I'm returning A, returning B, what could I possibly be missing in that switch? Default. Anybody want to hazard a guess?
Default.
No, that's the answer, yeah. I don't want to hazard a guess. Well, what you have to do is you have to dig into the Java SE specification, the language specification, and you will find that in section 13.4.26, it says, adding or reordering constants from an enum type will not break compatibility with pre-existing binaries. Essentially what they're saying here is that if I declare my enumeration in a separate source code file, and I compile it, and then I compile this code, it will work. But if I were to change my enumeration AB and add another value, recompile that and try and pass it in with a C, it won't work. So you have a question. Yes, you could. Yeah, but it's not actually the null which is the problem. A null would actually probably just throw a null pointer exception. When you try to
switch a null, does a switch null for a null pointer exception?
Yes.
Oh, okay.
Pretty sure it does.
It does.
Yeah, thank you.
I see somebody go. Somebody more knowledgeable than me.
On this very specific topic.
Right. So now we're going to get confused because of course we think, well, hang on. So this won't compile because it's got a missing return statement, and the previous example would compile even though we still have essentially the same situation. So if we go back to that one and we say, okay, well, AB, and we've got a switch expression, which does need to be exhaustive, remember, because it's a switch expression. So we think it's exhaustive, but we still have that same situation where I could have declared AB outside in a separate source code file. I change it later and then pass it in, and what happens? To answer that question, we have to dig even further into the Java language specification, and in the same section, you'll find that as with sealed classes, although adding an enum constant to an enum class is considered a binary compatible change, it may cause the execution of an exhaustive switch to fail if the switch encounters the new enum constant that was not known at compile time. Like I say, Alex Buckley is the man who's responsible for the Java language specification. He has to deal with all these little edge cases and things to actually specify. So it's an interesting situation where the exhaustiveness is slightly different in the in the situation of using a switch statement versus using a switch expression.
That also means that if this method were defined within the enum, like let's say some toString, pretty format class, yeah, it would compile fine.
I haven't tested that, but I'm not sure if the compiler is smart enough to know that. Well, I suppose it would be, wouldn't it? I would have to test that to see whether that would work. Yeah, because I don't know. I haven't tested it. It's a good question. Yeah. Right. So section 2, primitives in patterns. Okay. Now the important thing is obviously in Java we have the concept of primitive values as well as object references, reference types and primitive types. And as we well know, these things are treated differently. This was the whole idea at the beginning of Java, was that it was supposed to be an object-oriented language. They wanted everything to be an object, but they found that when they wrote Java, when James Gosling started out doing this, they couldn't get the level of performance they needed if they treated everything as an object. That meant they had to include primitives so they could deal with things as simple values. And this is where Valhalla's coming in, where we're starting to talk about value types and being able to use primitives in things like collections without having to use the wrapper classes and so on. But what we've ended up with is a situation where we do have both primitives and object references and reference types, including those wrapper classes. So we've got an int as a primitive and an integer as a wrapper class. And then we have this wonderful feature of auto boxing and auto unboxing, which was introduced, if I remember rightly, JDK 7, or was it 5? 5. Okay, yeah, JDK 5 introduced auto boxing and unboxing. Arguably not a great feature because it hides things. And you sometimes look at something and you go, well, that should do that. And then you realize, oh no, it's actually doing auto boxing or auto unboxing, and it's doing it under the covers. Since JDK 23, we can now include primitives in patterns. Couldn't do that before. It is still a preview feature. Yes, it is still a preview feature even in JDK 26. And I believe in 27 it's also going to be a preview feature, so it hasn't quite got to the point where it's a full feature yet. How and when exhaustiveness is required can sometimes require a lot of careful thought, as we will see as we go through. Similarly, when we talk about pattern dominance, mixing primitives and reference types makes for some very interesting situations. Right, so primitives in switch. So now what we're going to do is we're going to have our test int method, which will take an int primitive, and then we're going to use a switch expression, which will return a string, and we're going to have a case for byte primitive and a case for int primitive, and we'll print out whatever the result is. So of course, the obvious question is, will this code compile? Yes? Ooh, this is good. Oh, I like to see it. No? Okay, a few people think, not many people think yes, few people think no, and a lot of people are undecided. Okay, the answer is yes, it will compile, because it is exhaustive. If I pass in an int, and I've got a case for int, I am covering every possible value that I can pass as an int. So it is most definitely exhaustive. That will compile. Okay, what about if I have case byte, case int, and a default? Who thinks this will compile? Okay, who thinks it won't compile? Okay, and a lot of undecided. Okay, well the answer is no, it won't. Because, as it says here, I've actually put the error message you get from JavaOne. Switch has both an unconditional pattern and a default label. In this situation, the case of int is an unconditional pattern because it matches everything that we have. So if we match everything that we can possibly pass, there is no point in having a default. Default is essentially unreachable, so the compiler will reject it and it will say, no, you can't have both an int pattern and a default because you're duplicating it and you're trying to do two different things. Right. What about if we pass a value to the code that we know will compile? So we've got our case byte and our case int, and then we're printing out the result. So if I pass in 1024, who thinks we'll get the result byte? Okay, good. Who thinks we'll get integer? Okay, good. And some people think we won't get either of those, which is kind of interesting. So yes, we will get integer. But the important thing to understand here is what's actually going on. Now, because we're doing primitives, we actually have to do a runtime check. We're passing in an int, and we're passing a value of that int. Rather than simply matching against the type of that, we also have to test to see whether the value of that variable n will fit into a byte or will it fit into an int. So that's quite important. It's a runtime check that's going on. And we look at 1024, we say, will 1024 fit into 8 bits and a byte? No, it won't. So we can't match against that. Because it will fit into an int, because it's an int, then we match against that, so we get the result integer. What about if we pass in 42? Who thinks we will get byte? Okay. Who thinks we will get integer? Okay. We get byte. Again, it is a runtime check. We're not looking at it from a compile time perspective. We're looking at it at runtime. So whatever value we pass into that method, when we do the switch, the compiler has to generate code that will look at whether the value that we're passing in will fit into a byte or will fit into an integer. So in this case, 42 will fit into a byte. So we narrow it down and we say yes. We match against byte because that's the first thing in our list of cases. So we match against that and we get the right result. We get byte. What about if we cast 42 as an int? Okay, so pass that in. Will we get byte? Okay. Will we get integer? Okay, a couple of people there, right? What we'll actually get is byte. Because even if we cast that as an int, actually we're still passing it in as an int because the parameter that we're passing to the parameter of the method declaration is an int. So we pass that as an int, regardless of what we're doing, we're passing it as an int, gets passed as an int. Then we'll do the runtime check as part of the case to say, does 42 fit into a byte? Yes, it does. So we get the byte printed out. How about if I change it so now we have integer.value of 42. We create an integer wrapper class object and pass that in. So who thinks we will get byte? Oh, good. Who thinks we'll get integer? Nobody. Yes, we get byte. What is happening here is obviously we are creating an object reference, which is a wrapper class of type integer with 42 inside it. If we pass that to test_int requires, through the method signature, a primitive int. Now, normally you would say, well, there's a mismatch there because you're trying to pass an object reference to something that requires primitive. But the compiler will look at that and say, aha, I can do unboxing, auto unboxing. And it will say, I can unbox the value of that integer class object and create an int. So I pass in an int 42, and then I match against byte because it will fit into a byte. So it does the same thing. What about if we switch the order? So now we have case int followed by case byte. And we'll do the same thing, test int of integer.value of 42. Who thinks we get integer? Oh. Who thinks we get byte? Aha. Who thinks we get something else? Yes, we actually won't compile. Now, this is because what we're seeing is pattern dominance. Pattern dominance essentially says that if you match against a case and you prevent a match below, so you're dominating that, then it won't compile. So essentially what we're saying here is that if I pass in any byte value, it will always fit into an int. So I would always match against case int. I would never get to case byte. That's pattern dominance, because you're essentially making the case byte unreachable, which is illogical from the point of view of the code you're trying to write. So the compiler will trap that, and it will say, no, not going to compile it. Now, that makes sense, because you know, if you'd written that code and you were expecting to get to byte, you never were going to get to byte. Let's switch away from switch for a moment and go to instance of, because this is also something we need to just have a look at. So again, let's have our int x is 42, and then we'll do if x instance of int, print out int. Who thinks that we will get int? Ooh. Who thinks we won't get int? Nobody. Good. Yes, we will get int, because obviously int 42 Is X an instance of int? Well, yes, it is, because I've declared it as an int. So it definitely is an int. We get 42. If X instance of byte, print out byte. Who thinks we get byte? Ooh, who thinks we don't get byte? Okay. Right, okay. Yes, we do. Because a byte, 42 will still fit into a byte. So again, it's understanding that you're doing a runtime check. There's a runtime check going on to say, will that value fit into a byte? Yes, it does. Therefore, X, even though it's declared as an int. So it's not just pattern matching. Pattern matching is more about the type, as in a reference type, rather than a primitive type. So we say, is X an instance of byte? Even though we've declared it as an int, the value will fit into a byte. Therefore, it can be treated as a byte. I suppose you could also argue that that's similar to class hierarchy. So you could say, you know, is X of type string, instance of string, it's also instance of object. So you can match against either string or object. So in this instance, you can also match against byte. If X instance of byte, print out byte. If X instance of int, print out else. If X instance of int, print out int. Who thinks we get byte? Okay, who thinks we get int? Good. Prints int, no, byte. Int prints byte because 42 still fits into a byte. What about this? If X instance of int, print out int. Else, if X instance of byte, print out byte. Who thinks we get int? Who thinks we get byte? Oh, good. Yes. We will get int because it's the, in this situation, it's the best match. The first match. Yes, first match, not the best match. Because obviously we're saying, is it an instance of int? Well, yes, it is. 42 fits into an int. So no problem there. We can match against that so we don't get to the else statement there. So again, that's slightly different from the switch because there's no pattern dominance involved. You're using else if, and it will work slightly differently. Right. Let's mix primitives and reference types in the same switch and make your life really difficult. So now we're going to have test obj, which takes an object, because if we want to use reference types, we have to have a reference passed in. We'll switch on O, and then we'll do case byte B with the primitive byte and print out byte. Case integer, reference type, wrapper class, I, print out integer, and we'll have default, print out something else. So who thinks it compiles? Ooh, who thinks it won't compile? And then there's a lot of people who don't know. Okay, well, the answer is yes, it will compile. There's nothing wrong with that. Because we've got a default, then we are definitely exhaustive. So there's no situation. In fact, we do need to be exhaustive because we're using a pattern. So it's a switch. It's enhanced switch statement. So if I do test of integer.value of 42, I'm passing in a wrapper class object with a value of 42. Who thinks we will get byte? Ooh, who thinks we will get integer? Okay, and who thinks we'll get something else? Oh, okay. Right, we get integer. So what's happening here? What's happening here is we are passing in an integer object. It's a reference type. When we do the switch, the way the compiler, because we've got both reference types and primitive types involved, what the compiler is going to do is it's going to look for a situation which is unconditionally exact. That's the way it's described in the JEP, unconditionally exact. So in essence, what it's saying is, because we've got a case for a reference type, we're going to do a pattern match on that reference type. So do we actually have an integer object And yes, we do, because we passed in an integer that we just created. So it will match against that because it is an integer. So the pattern matching of the reference type is the important thing there. So we get integer. We don't get byte because we're not doing a runtime check to see whether we will fit into a byte, because we're dealing with a reference type rather than a primitive in this situation. Okay? That makes sense? What about if I do test obj 42? Who thinks we get byte? Okay. Who thinks we get integer? Who thinks we get something else? Okay. What we get is integer. What's happening here? So what's happening here is, was that? Yes, but there's a little bit more to it than that. So when we do test object 42, the compiler is going to look at that and it's going to say, need an object reference, so I will auto box it. But the subtlety that you need to be aware of is there's also automatic promotion involved. Automatic promotion basically says that when you want to auto box a value, it will auto box it, in the case of an integral value, either into an integer or a long. It will not box it into the best fit for that value. It will auto box it into either an integer or a long. So even though 42 will fit into a byte, it doesn't auto box it into a byte. It auto boxes it into an integer, which it gets passed into test obj, and then because it is an integer type, it matches against the pattern for integer as a reference type, and we get integer. How about if I say byte b equals 42, and then I do test obj of b? Who thinks we get byte? Okay. Who thinks we get integer? Who thinks we get something else? Ooh, okay. I like it. We get byte. Why do we get byte? Right, so in this situation here, the compiler is saying, okay, well, you've told me this is a byte. So I explicitly told it that it is a byte primitive. When I call test obj with b, which is a byte primitive, the compiler says, I need an object so I can auto box. But because you've told me that this is a byte primitive, I won't do automatic promotion. I will say, respect your wishes, and I will auto box it into a byte object. At that point, we pass it in, and then we do a switch on O. Now, we won't match against integer, because obviously it's not an integer type. It's a byte type. It's a reference type. We could match against default, but the compiler will look at this and it will say, we have a byte reference type which we can unbox into a byte primitive. And then we can match against that case, and then we print out byte. So that's why you get byte there. Okay, does that make sense? What about if I do test obj of 42? Yeah, test obj of 42. Yes, because I have now switched the two over. That's what I did. So let's have case integer first and case byte second, and then default. So if I do test obj of 42, think through the logic of what's happening there in terms of taking the value. Auto boxing is happening, maybe unboxing. So who thinks we get integer? Okay. Who thinks we get byte? Ooh, nobody thinks we get byte. And anybody think we get something else? Okay. We get integer. Now, this is really kind of interesting, because it's like, okay, how does that? So that's doing auto boxing again. So yep, so we're doing auto boxing into an integer object because we get automatic promotion. So pass that in and it matches against case integer. Question?
Because you're thinking of pattern dominance, aren't you?
Yeah.
Right. But, as I will show you in a moment, there is no pattern dominance.
Pattern dominance says that if, so you're thinking that because it can't get to byte, so that's unreachable, therefore everything matches against an integer. No. Because if I do this, if I make my, explicitly tell that the primitive value is of type byte, and then I do test object B, I will get byte. The reason for that is because, again, what's happening is the compiler is respecting the fact that I've told it it's a primitive byte, so it auto boxes it into a byte reference type. That gets passed in. It won't match against integer because it's not an integer, it's a byte. Then we get auto unboxing, and we match against byte as the primitive value, and so it prints out byte. So there isn't pattern dominance in that situation.
So you're saying that this, you remove case byte and something else, it would never match, that thing would never match integer?
Yes.
So if I took out the case byte B there, and I did this, I would get something else. Because, again, it's the difficulty of you have to think of this as being two different things in terms of the pattern matching, because we're pattern matching against a reference type there. So this is the unconditionally exact. It's always an integer. An integer is always an integer. That's the unconditional exact part. But in the case of the byte, we're doing boxing and unboxing. So the compiler's unboxing something which is a byte to get to a byte primitive.
If that was int and not capital integer, that would be the compiler error.
So again,
If you changed capital integer to just int, now you have a compiler error.
you would think so.
So, wouldn't you? You would think so. But I think you've actually, you may have jumped the gun a little bit with my, let's have a look at my next slide. Oh no, hang on. Hold that thought for just a moment. We'll come back to it. What about if I have integer I, byte B, int I, and then default? So would that compile? Yes? No. Okay. No, it won't compile. So it won't compile because that is pattern dominance. The reason that's pattern dominance is because if you pass in an integer, because you have to pass in a reference type, so if you pass in an integer, it will always match against case integer, so it's unconditionally exact. You would never be able to get to the case int because it will never unbox it into a primitive. So you always match against the case integer, so that is pattern dominance. Do you have a question?
What if you pass capital S short into test OBJ?
Hold that thought for a moment.
Do indeed. Hold that thought for a moment because we will come back to that. Case integer I, case short S, case byte B. So who thinks that will compile? Yes? Okay. Who thinks it won't compile? Okay, a couple of people. So was that what you were asking?
No.
Oh, okay.
Right, so I'll come back to what you were asking in a moment. I'll just explain this one.
So this one actually won't compile. And it says the case label is dominated by a preceding case label. This, I firmly believe, is a bug because of the same reason that if we didn't have the case short there, if you pass in an integer, it will match against case integer because obviously it is an integer. And if we pass in something which is a byte, it will match against byte because it'll unbox it and we'll get a byte as a primitive value. Obviously, if I pass in something that's as a short reference type, that gets unboxed and we should get short matched as the primitive value because you could put something in a short which won't fit in a byte, that would work. So I firmly believe this is a bug. And I actually talked to, I sent a message to the Amber mailing list, and this is one of the reasons why Brian was saying he doesn't like puzzlers. And I also I met up with Gavin Bierman, who's the person who's responsible in Oracle for this particular pattern matching and switch feature, because I was at the JCP Executive Committee meeting last year. And I showed him this, and I said, look, I sent this to the Amber mailing list, and I haven't heard anything back. He said, oh, yes, we've spent the last week looking at this one situation, trying to work out why it doesn't work. You're right, it is a bug.
Well, maybe transfer. Isn't short a type of integer? A short integer?
It is. But if I go back to this example, so here we've got a situation where if I pass in a byte as I say that I've got my byte as a primitive, when I auto box that to an object reference, or a reference type, I will get a byte wrapper class. So when it comes through here, it won't match against integer because byte isn't integer. So it doesn't match there. And then I get auto unboxing, which then gives me the byte. So if I come through to this bit, I should be able to pass in a short as a, I could even pass in a short as a, directly as a reference type. That gets unboxed and would match against short. So I don't see any situation where that is actually pattern dominance. So coming back to your question, you were saying short?
Yeah, so we went to the previous slide. Not this case, there's no, okay, no explicit short case. And now though, we pass a capital S short object into this method.
Right.
It goes, you know, and it's got a value.
Yeah, so if you pass in a capital S short object, a reference type, short reference type, that will match against default. Because it isn't an integer, short is not integer. Because remember, we're talking about the actual type now, not the value. So it doesn't match against the integer, not unconditionally exact. Even if you unbox it, a short won't fit in a byte, so that won't work. So it must then match against default.
Does it make a difference if we pass in a capital S short and we replace an integer with an int in the first line?
Yes, that would definitely make a difference. So if you had an int, if you had a primitive int there, and you pass, yes, hang on. So if you pass in, right, yes, yeah, okay. So we're still passing in an object as the parameter, but we change it to primitive int there, and we pass in a short as a reference type. At that point, the compiler would do an unboxing, and it would then do a runtime check to see whether the value of that short would fit into a byte. If it did, it will match against byte. If it didn't, it will match against int, even though it's a short. So
Does that make sense?
No, but that's
In here, if it was the class type, that would be,
yeah,
would it combine?
yes, because remember we're getting unboxing happening here, because we have to pass in a reference type. So you have to pass in a capital B byte object. Oh, see, in this, you had a capital B.
Yeah.
Right, so if we had a capital B byte, and you pass in what? Oh, yes, yes, because you've got a default. So if you have integer and byte as types, then by having a default, you are exhaustive. So you... No. No.
Extend byte, no vice versa. So
True. Yes. So if that was a capital B byte, it would compile because it is exhaustive, and the integer is not dominating byte because they're two separate types and they're not subtypes. So yeah, that would work. Okay. Yep.
Would the one, the next one that you're calling a bug, would that compile if you switch the order of short and byte?
Just get to it right. Okay, this is the one. Yep. Yeah.
Switch the order of short and byte, then would it compile?
In that case, it shouldn't compile because you would have pattern dominance.
But would you have pattern dominance? Because you could still pass capital S short and it would like exact match against the short.
Not in this case, because in this case, if you pass in anything that's not an integer, it would have to unbox it. So if it unboxed it, so if it's either short or a byte, it has to unbox it first to match against case short primitive or case byte. So if those were reversed, the No, hang on. That wouldn't compile because the short would be dominating the byte. If you reverse them, in theory, it would compile. Yeah, it would compile. No. Yeah. Yes, because I tell you, thinking this stuff through is tricky. But yes, it's because we're doing in this case, you have to unbox something that you passed in. So you either unbox a short or you unbox a byte. So you could match against the short or the byte. But you don't get pattern dominance there because the unboxing is the thing which determines which one is going to get matched. So if you pass in a byte, it will get unboxed to a byte, and so the short doesn't dominate the byte. That's what I'm saying.
The notion of unboxing or primitive, if the compiler checks to see if it's unboxable, if you passed a string, you're not going to try to unbox a string.
Yeah, so if you pass in a string, it would go with default because you can't unbox a string, so it doesn't. There's no chance of it matching against a primitive. So it doesn't match against integer as an exact. It doesn't match against either of those because you can't unbox it, so it goes to default. Yeah. Yeah. This is where unboxing and boxing becomes somewhat difficult because you have to remember all these things that are happening there. Okay. Yeah, so that was the one I said, yeah. All right. What about this one? So now we're going to have, we're going to go back to using primitives again. So I'll have test int, and we'll take get int n from get value, and then we'll switch on primitive, and we have case integer I and case byte b. Now, what do you think happened? Will this compile?
Who thinks yes? Who thinks no? Okay. Yes, it will. And this again is a bug. Because if you actually, I tested this, and because I was looking at this, I'm thinking, well, hang on, so we're dealing with primitives now, so I've got an int here, so I get the value, so in order to match against an integer, I have to box it and get an integer. And literally, compiles like all values will print out an integer. So whether you pass it in a value which will fit in a byte, a short, or an int, you always get integer. So by definition, that means that case integer is dominating case byte. So it shouldn't compile because there's pattern dominance involved.
What happens if you change
So
if
again,
you made n a long?
right. That wouldn't compile because it would be exhaustive.
Because if you got a long, you could pass in a value which is not an integer, wouldn't fit into an integer or a byte. So why do I compare? Oh, because it's a good question. Because it's a switch. Because it's a switch statement, but it's an enhanced switch statement because you're using pattern matching, which wasn't available before. So it is classified as an enhanced switch statement. Therefore, it does have to be exhaustive. Yeah.
This is going to sound kind of negative, but why did they add this to the language? Like, what's the use of this?
Well, it is very useful to have the ability to match. A pattern matching on types is very useful because it extends switch to being able to use types. It is also very useful to have primitives because you might want to, there are various examples if you look at the JET for this in terms of using primitives to be able to match against different combinations of primitive values. The issue arises when you try and mix them, as we can quite clearly see in the examples I've just showed you. So this is what I would say, even though technically the specification allows you to do this, I certainly wouldn't recommend it because it doesn't really make sense. So, when you say, why did they add this to the language? It's more as that they wanted to add reference types and they wanted to add primitives, both of which make sense on their own. But if you mix them, it gets very complicated.
The compiler could disallow that, just anything.
I suppose, yeah.
You see, that would be a simple way of doing it, is to say you can't mix. But then that sort of the argument against that would be, well, that then overrules the idea of auto-boxing and unboxing, and you know. But yes, it's certainly an argument that you could make, which is to just prevent people from using both primitives and reference types in the same switch. It would be a reasonable argument to make, yes. Okay, so section 3, I think this is the last section I've got, yes. Guarded patterns. Okay. Right. Now, guarded patterns are things like this. So we've got, again, int x, where we're getting a value from somewhere, and then we're going to do a switch expression. We're going to return a string, switch on x, and we'll have a case for 0, which will return 0. We'll have a case int I, and we're using a guard, which says when I is less than 0. So guard essentially says match on the type, and then look at a predicate, which evaluates true or false on the right-hand side of the when. And if you both match against the type and the predicate, then you do what's on the right-hand side. So we say case int I when I less than 0, d is negative, case int I when I greater than 0, positive. So who thinks this will compile? Who thinks it won't compile? Okay. Would you like to say why it won't compile?
I'm not up on this latest syntax, but in case 0, you're just returning a string, and in the case int I, you're going to d equals.
Yeah, okay, that's my fault. It shouldn't be like that. Yeah,
because yeah, neither of those should have d equals in there because we don't have a d. That's a typo on my slide. Well done for spotting that. So it shouldn't be d equals. It should just return 0, negative, or positive. So hang on, let me. Do I get that? Yes, hang on. I'm just going to swap my displays over again. Right. Okay. Now, who thinks this will compile? Who thinks it won't compile? Does anybody think it won't compile?
The compiler's not smart enough to know you don't need case int I when I equals 0. That's my guess.
very good.
You're absolutely right. So the answer is it won't compile. And it says the switch expression does not uncover all possible input values. It is not exhaustive. So essentially what you're saying is it's not smart enough to evaluate the guards on those cases. So the compiler does not evaluate the guard to determine exhaustiveness. What it will look at is it will say, okay, you've got a case of 0, you've got 2 cases which have int I, but with a guard, don't know what the guard is, don't care what the guard is. So even though us looking at it logically, we say, well, 0, negative, or positive covers every possible situation that we can pass in. Compiler doesn't look at it that way. It looks at the fact that there is no unguarded int. So there's no, from its point of view, there is a missing part where it thinks there could be a value that could be passed in which won't get caught, and therefore it, so you get the fluffy juice. Let's see if I can. Right. Okay. Yeah, now we're going to go back to mixing. Yeah. Right. Switch on X. I hope I've got this right now. Case integer I when I greater than 0. So we've got a guard on a reference type pattern match. We'll print out positive. We'll have default negative and case 0, 0. And then we'll print out the result. So we are returning, we're returning D, print out what the D is. So positive or negative on 42. Who thinks we get positive? Nobody? Okay. Who thinks we get negative? Who thinks we get 0? Okay. Who thinks it won't compile? Oh, okay, that's the, right. Well, it will compile, quite happily. and it will give you positive. Now, this is interesting because, again, like I said, the syntax of the switch statement came directly from C. And I must admit, I didn't even realize this myself when I put this slide together. You don't have to put the default at the end. You can put the default anywhere you like in a switch statement. And that's important because essentially what the compiler is going to do is it's going to generate code which says evaluate all the cases first, and only if none of those cases match, you go to the default. But how you specify that in terms of your order doesn't make any difference. Yes, the order of the cases does, because you might have a match in a different way, but the default can go at the beginning, it can go in the middle, it can go at the end. It doesn't make any difference to the actual code. So that will compile quite happily, and because we have a value of 42, what's happening is we're passing in 42, but here what's happening is it's saying, 42, case integer. Well, I can box 42 into an integer wrapper class. Test when I is greater than 0. Does the value of I inside the wrapper class, is it greater than 42? Yes, it is, because actually technically you're unboxing it there at that point, and then say it's positive. So that will match against that and give you positive. What about if we do positive or negative -1? Who thinks we get positive? Okay, who thinks we get negative? Who thinks we get 0? Yes, we get negative, because again, what's happening is we're passing in -1, fine. It's doing an auto boxing there, says, is I greater than 0? No, it isn't, so it doesn't match against that. We don't look at the default first because, we don't look at the default first. We'll look at the case 0, doesn't match against 0, so it becomes negative.
When the value was 42, I believe.
Yep.
So it will first check for the boxing integer,
Yes.
but then on the second, the when clause,
Yep.
it will use the value passed as is it. It will not convert the boxed value to unboxed, right?
No,
It would actually test it. So it will box it first and say, okay, so turn that into an integer, but it will then execute the guard, and the guard will then say, okay, it's not greater than 0. So then it drops.
Will it use the boxed value or the unboxed value in the when?
So it uses the unboxed value when testing I greater than 0.
The one that was passed, not the one that was converted.
I think in this situation it's a little difficult to. I'd have to look at what the compiler actually generates, but I think what happens is it will box it and unbox it in the same thing. So it will box it into, because you've got a reference I there. So I in this situation is an integer wrapper class object. So when we do the test on I, in order to test if it's greater than 0, because it's an object reference, it has to unbox it to get the primitive value out to test if it's greater than 0. So there's both boxing and unboxing going on in the same line there.
It was integer I, when X, that will be a compilation error then.
Yes. Yes. Yeah. If you had a, I think, so if we passed in integer X.
Integer X, and instead of I greater than 0, if it was X
No,
greater
than 0.
No, because then
We'll still do unboxing, because we're trying to do a test against a primitive, and because it can unbox it, it will unbox it. So even if you had a reference type being passed in, you could match against the integer I, it would still be an integer I, and you'd still do unboxing to test against greater than 0.
Just to clarify or confirm, the I greater than 0, if it was coded as X greater than 0.
Would have the same result, because essentially you're just getting the same value. Yes, if you said when X greater than 0, all you're doing is avoiding the unboxing. Yeah. Right, yeah, so we get -1. No, negative, yeah. Okay, positive or negative on 0. Okay, this hopefully should be fairly obvious. So who thinks we get positive? Who thinks we get negative? Oh, okay, and who thinks we get 0? Right, and we get 0. Because again, what's happening here is we're passing in 0. It will do Auto-boxing generates object reference I, tests I greater than 0 by unboxing it, but it's not greater than 0. It then tests against case 0. Yes, it is 0. Matches, so we get 0. Don't need to go to the default. So that works. What are we doing here? Okay, yes. Aha. Right, case integer I when I greater than 0, positive. Default, negative. Case integer I when I equals 0, return 0. So who thinks we get positive? Who thinks we get negative? And who thinks we get 0? Okay. Anybody think it doesn't compile? Ooh, it doesn't compile. So this is one of those. This is one of those. This is one of those ones where I had to really think about this and go through this in quite some detail. Right. So the error message you get, this case label is dominated by a preceding case label. That's what you get from JavaC. If you look at what IntelliJ gives you, it's actually more meaningful. So IntelliJ is really good because it gives you slightly better error messages than JavaC. So IntelliJ says label is dominated by a preceding case label default. So it's saying that in here, the case integer I, when I is equals 0, is being dominated by default. But it's like, hang on, I said it doesn't matter where you put the default, because you can put the default anywhere, and it's only if it doesn't match against any of the other cases that you go back to the default. And so you think to yourself, well, hang on, how does that work then? And you have to, again, dig into it, and you find that for patterns, where we're dealing with type references here, Java evaluates cases strictly from top to bottom, and that includes the default. Now, why they did this, I don't know, but this is how it works. So you have case integer I when I greater than 0. Because you put the default in the middle, that is dominating the case integer I when I equals 0, because it is a pattern rather than case 0, which is just a switch on a value.
And sorry, so in the previous slide, when you had the mixture of pattern and not a pattern, then default works.
Yeah,
like
Because the default is after the pattern, if you put the default before the pattern, you get the same problem. But because you put the default after the pattern, but before a case on a constant, then it will compile and it will work. But because in this example, we're not using a constant, we're using a pattern. When we do patterns, Java evaluates cases strictly from top to bottom.
Now, a question about the previous slide. So if we say I greater or equal 0, then
yeah. So
In that case, I may have a hold that thought for a moment. We'll come back to that. Yeah, because I think my next example might answer that question. Yeah. You know, so we got that one. So that one's patterns. Java evaluates cases from top to bottom. Right. Okay. So now the next one. Aha. Yes. So I think this is exactly what you just said. So if we do almost what you said. So we have case integer I when I equals 0. We print out uppercase 0. Default is non-zero. Case 0 with a constant, print out 0 in lowercase. So if we do positive or negative on 0, I told you, I said if we start off easy and we get to a point where you're going, I don't know what it does. So if we pass in 0, who thinks we get capital 0? Okay, who thinks we get lowercase 0? And who thinks we get non-zero? Well, the answer is we get uppercase 0. So in this situation, again, I had to look this one up because I was like, hang on, how does it deal with that? And the situation is guarded pattern labels don't dominate constant labels. So essentially what it's saying here is that, again, it's that evaluation. The compiler doesn't look at what the guard is actually doing. It simply says, oh, you've you've got a default, and you've got a case of integer with a guard, and so long as you've got a default, that means that all values are covered.
Yeah, but going back to C rules, you basically have two same cases, don't you? 0 twice. You couldn't do that in C. You couldn't do that in Java, even in the regular switch statement. So
Yes.
why would that even compile?
Because, as I say,
We're looking at it from the point of view of we see that the guard predicate is testing to see whether I is equal to 0, which is the same as a constant 0. You agree? But from the compiler's perspective, all it looks at is I've got a case integer with a guard. It doesn't evaluate the guard. So it's not saying, oh, you've got I equals 0 there and I equals 0 there. So it's two orthogonal. Yes, it is. Yes, completely. Yeah. Right. Yes, last one. Right. So what about if we do this? So we say now we got case integer I, which is unguarded, and we'll have positive. Default is negative, and case 0 is 0. And we go positive or negative on 0. So who thinks we get positive? Right? Who thinks we get negative? And who thinks we get 0? Oh, okay. Who thinks it doesn't compile? Oh, a few people. Okay. Anybody want to guess why it doesn't compile? Okay. What's that?
You can't get to 0.
Oh, hang on, I went the wrong way. Sorry. Right, yes. So this case label is dominated by a preceding case label. And again, label is dominated by a preceding integer I. So in this situation, because it's not guarded, again, it's this mixture of things where you've got both a pattern, which is unguarded. I mean, the compiler then says, okay, you've got integer I, and then you've got case 0. So at this point, it can say you've got a dominance. With the guard, because it doesn't evaluate the guard, it simply thinks, oh, there's a possibility that that guard will not match, and therefore you can get to the case with a constant. But if you take away the guard, the compiler can logically infer that because 0 is an integer, it will match against integers, so that dominates that. So it does actually make sense in terms of the dominance. So just to summarize then, modern Java features add a lot more power. I know that I've shown you some kind of strange examples and things that you shouldn't do, but essentially the whole idea of pattern matching, the whole idea of using switch expressions, having patterns in switches and so on is very powerful. It does give you a lot more things in your toolbox to be able to write code in a more succinct way and a more reliable way as well, I think. Sometimes things don't quite behave the way you expect them to, as I think we have definitely demonstrated with the examples that we just went through. Almost always, this is logical and well thought out. Certainly, as I said, the problems that they have in trying to match the two things together, where you've got both primitives and reference types, and dealing with auto-boxing and unboxing, makes it quite a nightmare to get everything to fit together and work in the right way. In some cases, preview features need to be changed before they're becoming final. So I think one of the reasons that they haven't made primitives in primitives in patterns is not quite final yet is because they're still going through all of the edge cases and trying to make sure that things work in the way that they should do. And the IDE will help you a lot because, like I say, you get more meaningful messages from IntelliJ than you do from JavaC. So with that, thank you very much.
Thank you, Simon. That was awesome. Awesome. I didn't get any of them right.
You must have got the first one right.
So again, thank you to TerraSky for sponsoring us and for sponsoring the remainder of the year. Thank you to Hazelcast for sponsoring the pizza. Thank you, Hazelcast. And next meeting is September 17th here, and it's going to be on putting spec-driven code into production, spec-driven AI code, Java code into production. Yeah. Oh, IntelliJ license. I know, but I'm trying to get the speakers for next week or next month. I've forgotten the speakers from Jakarta. Anyway, you'll get my email. Who does not have an IntelliJ license? That wants one. That wants one. Yes.
Those features, what version they are? The ones that you just discussed, what Java version?
Oh, so that actually covers quite a number of different versions. So it's pretty much all the way from 21 through to 26. Different parts of it, so like switch expression was introduced much earlier. Patterns was introduced, I mean, since JDK 23, we've had primitives. So yeah, there's various features have been added over time.
Sorry, any other questions for Simon?
Yeah, those two things that you mentioned, you felt were bugs.
Yes.
I'm with you on that one. Are they actually reported as bugs officially that you recognize as such?
I must admit, I haven't seen like a bug report on the bug system. But like I said, I did talk to Gavin Bierman about it. He said, yes, we are aware of it and we're working through, because sometimes it's not easy to sort of file a bug on stuff like that. But he said it was really good that the fact that they have a nice, succinct piece of code that demonstrates the problem, so then they can kind of drill down on that and figure out what's actually going on.
Garrett Grunwald and Ivar Grimstead. So from Jakarta, and Azul and Jakarta next September.
Oh, that's right. Garrett's coming, isn't he?
That's right.
Ivar.
On spec-driven AI development with Java, of course. IntelliJ licenses. So who wants an IntelliJ license? Do I have 5?
More hands than we usually have.
I think we have a bunch. We have enough, yeah. So send an email to info@javasig.com. Just say, like, I need an IntelliJ license. And with that, I'll see you next month. Have a good rest of the summer. Thank you.
Thank you.